Hello, my name is Adam Gray, and welcome to MCAT Scientific Reasoning, Lesson 2.2. And you should be really excited for this lesson because of all the lessons in your MCAT course. This lesson is the highest yield in terms of if you master what's in this lesson, if you master the learning objectives here, it will get you the most points on test day. Skill 2 questions are 45%, almost half the questions on the science sections of the MCAT, and this is the biggest lesson on Skill 2. We're going to see some challenging, meaty questions that have some wonderful solutions, so let's jump right in. This lesson has fully 4 learning goals that we're going to tackle. The first 2 focused on scientific phenomena, and then the second 2 focus observations and theories so that we can draw conclusions about science. These concepts, scientific phenomena and observations and experiments, are what the MCAT defines as scientific reasoning. And that's why all of these learning objectives are gathered together in this lesson, because as you'll see, there are a lot of connections. All of the questions that we're about to see are about the causes and effects in systems based on scientific rules and principles. The specific scientific rules and principles that we'll be seeing and answering questions in the context of are chemical kinetics, solubility, and acids and bases. You'll probably recognize these as some of the more challenging, juicier topics in MCAT general chemistry, and that's why they're perfect to help teach us about scientific reasoning and see what sort of critical thinking is involved in that process. Let's start out with the first learning goal, which is one of the ones about scientific phenomena, and specifically determining the likelihood of that phenomenon, meaning did it happen or not? Will it happen or not? But before we even see that, you should know what we mean and what the AAMC means by phenomenon. A phenomenon in our usage is a specific occurrence that is in an MCAT question. So it'll be a specific experiment or example where you'll have to apply scientific principles and reasoning. Let's see exactly what that means with question number 1. So question number 1 gives us a nice big chemical mechanism, 4 whole steps right here. And it asks us, is acid acting as a catalyst here? So by the definition of phenomenon, the answer to the prompt here on the page, that the phenomenon being asked about is acid acting as a catalyst? Those are the exact words the question uses. You may even see in the answer choices, they're of that classic pattern of 2 yeses, 2 nos, and then some reasons. So before we give the rest away, go ahead and try to answer this question yourself using the mechanism. Apply what you know about catalysis to this specific situation, and there'll be a few steps before you get to the answer, but go ahead and try to find that answer, and then we'll go over it. So what it is you might have immediately recalled about catalysts is 2 things. By definition, catalysts help reactions move along. That is, they decrease the amount of energy that a chemical system has to take in to push the reaction forward. Enzymes are a really good example of a catalyst. But also, by definition, these catalysts have to be regained by the end. They get put in, but they have to then come out before it finishes so that they can then catalyze another reaction. Otherwise, it's not a catalyst, it's just a reactant. The way we apply this principle to this question is by looking for acid. It's pretty clear that it's right here in the reactant, so we've got an H+, although it could just as easily be written as an H3O+, the hydronium ion. But then, if you look at all the products, that acid never comes out again. So the answer is D. No, acid is not a catalyst because it goes in, but it doesn't ever come out again. Choice C, which does also say no, says no for the wrong reasons. In the absence of nitric acid, this reaction wouldn't go forward at all because nitric acid, the hydrogen in it at least, is one of the reactants. And of course, this question requires a lot of competencies like knowing what a catalyst is and being able to look at all of these chemical reactions and see what's going on. But the real thing to learn here that we'll see expanded on the next question and many other questions you'll see in your practice is the structure of this question. We were asked, is this certain thing happening? And here we were able to say no, based on the science that we know and connecting all those dots. Let's move on now to question 2. This time, you answer the prompt on your own. What is the phenomenon, the specific scientific occurrence that this question is asking? Does it happen or not? The phenomenon here is precipitation, specifically of this silver thiocyanate, which you don't even need to know the name of that, but AgSCN. In order to answer this question, you need to know in what situations do things precipitate. And you may already know this, but precipitation happens when the ion product, or the product of concentrations of ions, is greater than the KSP of the solid product of those ions. In this case, the relevant KSP is given in the question. It's 1 times 10 to the negative 12th. So given that knowledge, apply the same skills to this question of predicting whether or not this phenomenon happens that we did back in question 1. Take this question, move through the answer choices, and pick the one that you think is right. So the work that you probably did here is that you wrote down, just as you should write down on test day, that ion product for silver thiocyanate is the concentration of the silver ion times the concentration of the thiocyanate ion. But this is the point where this question can go 2 routes. One route is for you to calculate the exact value of these concentrations by using some stoichiometry and some unit conversions. But the other one, which is a much faster way to answer the question and to leverage mastery of this subject, is to work with a rough approximation first. Because we're already given 2 concentrations of these solutions. The sodium thiocyanate solution is 1.0 times 10 to the negative 5th, and the silver nitrate solution is 1.0 times 10 to the negative 5th. That means if we're mixing them together in anywhere near equal proportions, the ion product is probably something like 10 to the negative 5th times 10 to the negative 5th, which means in total it's 10 to the negative 10th, give or take. If you compare this number to the KSP given in the question stem, it is clearly greater. 10 to the negative 10th is 100 times greater than 10 to the negative 12th. That's a very strong prediction to bring you to the answer choices, and the correct answer is that yes, there will be precipitation because there are more ions in solution than can be easily dissolved. Now, if you did go ahead and do this math, the exact ion product is actually 1.9 times 10 to the negative 11th, a little bit less than 10 to the negative 10th, but still greater than 10 to the negative 12th. Now, we're not going to linger on the math approximation that was done in this question, but I'll leave it at just the fact that this kind of approximation and estimation is exactly what you should be doing on questions like this in your practice and on test day. At the very most, you may want to double check things, maybe even at the end of a passage or the end of the section that you'd find this question, to make sure there wasn't something you totally overlooked that would change the answer. But the MCAT does tend to give us numbers that allow us to estimate safely like this. The more important takeaway for this question is it has the exact same structure as question 1. This is a question template the MCAT will use over and over, where they'll say, hey here, something might be happening. Is it happening or not? And it asks you to apply what you know about that science and apply a little reasoning on top of it to this specific situation to find an answer. Success on these questions depends both upon your mastery of the science and your familiarity with questions like this. We'll now move on to Learning Goal 2, which is similar to Learning Goal 1 in that it covers scientific phenomena, but different in what it asks about them. This time we're going to be given the phenomenon and the fact that it does happen, but we're going to be asked to explain why it happens. What are the underlying aspects of the science that make this happen, or what is likely to happen next, given the scientific principles you know? The first example we have here is question number 3. For this one, try it all yourself first. Answer the prompt on the page. In other words, what is the phenomenon being asked about? Just the same question that got answered in questions 1 and 2. And then also go all the way to an answer. Then we'll see the inner workings of this question so that we can apply this reasoning to other questions. This one asks about ideal gases. Doesn't call out the name exactly, but it does mention both concepts. But the phenomenon itself is not ideal gases per se, but when gases don't behave ideally. And then we're asked for a specific comparison between helium and carbon dioxide. And this is very indicative of what Skill 2 scientific reasoning questions that you're going to see a whole bunch of on your MCAT are going to ask you to do. Not just say, hey, do you know about ideal gases, but specifically what part of ideal gases is necessary here. Because when you're getting asked about deviation from ideal behavior, the most important aspects of ideal gases are the assumptions that we make in the first place. Now, there are several assumptions, but the ones that hopefully come immediately to mind is that they assume no intermolecular forces like van der Waals or dipole-dipole interactions, and that gas particles have no volume. Now, obviously neither of those is true in the real world, and that's exactly why gases deviate slightly. Once you move through the Roman numerals for this question, the only one of these three that comports with the facts and principles of ideal behavior is Roman numeral 2. Carbon dioxide has larger intermolecular forces than helium, which means it's going to deviate from that assumed no intermolecular forces more so than helium is, which agrees with the phenomenon in the question stem and what we know about ideal gases. Roman numeral 1 is wrong because CO2 particles don't actually have lesser volume, they have greater volume. And number 3 is wrong for a number of reasons, probably the most important one being that helium molecules do not necessarily have higher kinetic energy than CO2. We're not given enough detail in the question stem to know which way we should go, but it really could go either way. If helium's at the same velocity than CO2, it actually has lower kinetic energy because it has less mass. But if helium is at the same temperature as CO2, then they have equal kinetic energy, because temperature is an expression of kinetic energy. Either way, Roman numeral 3 doesn't deal with either of these important assumptions, and so it can be eliminated. But the key to the skeleton of this question to take away is that it not only demanded that you recall scientific principles, but that you dig into those scientific principles to explain one specific exact occurrence. This question doesn't just ask, how do ideal gases work? It asks, how do ideal gases work in relation to CO2 and helium? And so because there's one level removed, so to speak, with that specific example going on, there is that level of reasoning you need to use to connect what you know with exactly what's given to us in the question. Let's apply the same structure to another question that is even longer. Whole lot of text on this one. First off, read just the question stem and fill in the prompt that's on the screen here and on the page in your book. What is the specific scientific phenomenon that this question is asking us to explain when it asks why? The phenomenon here is neutralization in titration. The setup that's given is that we have an acid, exactly 385.43 milligrams of it, that we then titrate and neutralize with a base, sodium hydroxide to be specific. And the phenomenon we need to understand to answer this question is how exactly that neutralization happens and what are the rules underlying it. Because the question tells us, and maybe if this is a familiar subject for you, this is something you already know, it doesn't matter how much water is in the solution. That is, if you use 0.1 liter of water versus 10 liters of water, it's going to take the same amount of NaOH to neutralize the acid. And why is that? So now that you've got this question stem put together, make a prediction and then pick what you think is the right answer, and then we'll go over it. The correct answer here, which is a pretty clear match to a reasonable prediction, as long as you can read through the answer choices, is choice C, which says all that matters is how many moles of acid are involved, not the concentration of the acidic solution. And this is true. This is an application of knowledge you probably have about titrations, which is that if you have a certain amount of acid, in this case 385.43 milligrams, in a titration you sit there and drip, 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 drip the sodium hydroxide until you reach the equivalence point, that really steep point in the titration graph. But what that point represents is an equality of moles between acid and base. Notice that in that entire description, there's no water involved. The solvent actually doesn't influence things at all, because that fixed amount of acid is going to neutralize a fixed amount of base. We're not given the exact strength or identity of this acid, but whatever its strength is, it has a certain number of moles of hydrogen in it. And those excess moles of hydrogen that get neutralized by the sodium hydroxide are going to be the same no matter how much water you dilute it with. Because water, or at least the kind that we use for titrations, has an equal proportion of hydronium and hydroxide ions. So when you add the water, those two effectively cancel each other out. So what this question and the one before it have asked is not just do you remember the science, but can you explain why the science works the way that it does? So whenever you have a question that has long answer choices or has the word why as the question stem, which you're going to see a lot on your MCAT, it's going to require these same deep levels of science knowledge, reasoning, good reading of the question, and so on, that this question and the previous one demanded of you. In this learning goal, we're going to build upon what we've seen in the first two and look at the third aspect of scientific reasoning as the MCAT defines it. Specifically, we're going to move from mere phenomena into scientific theories and how new evidence or observations will influence those theories. Because that is, after all, what science is all about. See something about the world, you make a theory that explains it, and then you continue observing the world and you see if that theory is supported or perhaps even called into question. We're going to see examples of both of those here in this learning goal. What we have on these next 2 pages is a passage, more accurately a passage excerpt. It's shorter because we don't need a whole passage for our purposes here. And then 2 questions that are about new observations and theories. So at this point you must be old hat at reading passages, especially when one is short, and this one's kind of fun too. This might remind you of some experiences you had in middle school science class. So go ahead and read and outline this passage to yourself now. Okay, now we'll review this before we move to the real meat of the questions. This passage is about Van de Graaff generators. I don't know who that Van de Graaff was, but he sure liked having these things that made your hair stick out when you put your hands on them. This paragraph more or less explains the generator itself and gives a guideline to the figure. The figure gives us a structure of the generator, and the main takeaway in terms of science content is that we have negative charges. There's negative charges here on the belt, and they move up the belt, and eventually they make it into this dome, and then the negative charges travel from the inside to the outside of the dome, build up on the outside of the dome, and then if you as a person put your hand on the dome, it generally makes your hair all frizzy. Because of course those electrons move onto you and your hair and so on. If you don't know what I'm talking about in terms of the frizzy hair and you didn't have the experience of a Van de Graaff generator in your middle school science class, it's something you'd certainly look up on the internet. Pretty funny. MCAT science in action. Anyway, this passage finishes up with 2 predictions that a hypothetical student has about this generator. The first prediction is that the charge on the dome increases indefinitely, increases forever. We'll see there might be something wrong with this prediction later, and if you thought that, if you predicted that there might be something wrong with this prediction, then good catch. The second prediction is about a field, an electric field. The student is predicting that you could measure this field because it causes the negative charges to move from the belt to the dome. And this type of passage is not atypical of the MCAT. It's a little bit less medically based than many MCAT passages, but the idea of a situation and then a couple theories related to that situation is very common because it allows them to ask you questions like the ones we're going to see. We'll start with question 5. What we're going to do with each of these questions is identify what the new observation is, but then of course try to bring it to an answer. This question is asking about prediction 1, but it introduces a new observation. Answer the prompt in your book. What is the new observation in this question? The new observation is that all that negative charge will leak into the air, and the negative charge will charge up air molecules, and the negative charge, the electrons, essentially leave the edge of the dome. And of course, if an electron leaves the dome, it's no longer on the dome, meaning the charge is lost from the dome. But the real question is, how does this affect prediction 1? And the basic yes or no answer to that question, does it support or weaken prediction 1, is going to allow us to eliminate answer choices. Because, as you probably noticed in assessing this question, the answer choices are 2 yeses and 2 nos. So the first question is this: does this observation strengthen or weaken prediction 1? It weakens prediction 1. Prediction 1 says that charge will build up infinitely on the dome. But this question stem tells us, the student learned, that charge is actually lost from the dome. Dome loses charge, it's not going to build up infinitely. That means right away you can eliminate B and D because the answer is no, this fact doesn't support prediction 1. But now let's take it to the final answer. Read choices A and C and pick which one is correct. The correct answer here is C. Charge does not build up indefinitely. It actually builds up to a certain point. It's asymptotic. It builds up to a certain maximum because eventually just as much charge will get lost to the air as is put onto the dome from the belt. Input will equal output, and therefore the charge won't build indefinitely. It's actually a very interesting application of equilibrium. Choice A is wrong because it's got the logic a little confused. The belt on the interior of the generator isn't suddenly going to know that air has started to ionize. The belt is going to act just like it always has. So there's not going to be anything special about that moment for the belt. There's always going to be a little bit of repelling because the belt is negatively charged and the dome is as well. But the entire point of the generator is that that charge is denser on the belt, and so it moves from the belt to the dome, and it will continue to do that even once the air begins to ionize. It'll just eventually reach equilibrium, as choice C tells us. So we've seen an observation weaken a prediction. Now let's see observations that strengthen predictions, specifically prediction 2. This question tells us the observation that made the student form prediction 2 in the first place. The student saw that the negative charge on the dome keeps going higher and higher. Even though there's already negative charge on the dome, usually negative repels a negative, but that negative charge keeps on building up. That's what caused the student to believe prediction 2, because the dome charge builds up, it's not repelled. Remember, prediction 2 was the one that said there is a measurable field that brings electrons from the belt to the dome. But importantly, this question also asks for another observation, a plausible observation that would also support prediction 2. So this is kind of the other way around from question 5. Question 5 gave us a new observation and asked if it supported a prediction. Question 6 gives us the prediction and some evidence supporting it and asks us to find another observation that also supports it. So in this case, the answer choices are predictions rather than strengthens and weakens. Same basic logic is involved, but the MCAT switches it up. So now, give it a shot. Read these answer choices and find out which one of these choices would also support prediction 2. The answer is B. It actually explains to us why the Van de Graaff generator is shaped like a dome in the first place. Because the dome is spherical, the electrons on the belt don't feel a repelling force from any one electron on the dome, because any force it feels from one side of the dome, it's just as easily feeling from the other side of the dome. That means the electrons on the belt are free to just get repelled from each other and shoot off to the dome. And if you got this question right, you may have picked B because it matched a prediction or you really understood B when you read it, but you also might have eliminated the wrong answer choices. Let's see how the wrong answer choices don't support prediction 2. Choice A is wrong because the potential can't be zero inside the dome. There's so much charge all over the dome. The potential, remember, that's KQ over R. Q is going to be really big. There's a lot of charge in there, and there's nothing that's going to cancel out that Q. Remember, potential, electric potential or voltage, is not a vector. So two potentials in two different directions can't cancel each other out. Potential is not zero. Choice A is just a false statement, so it's got to be wrong. It's not a plausible observation, as the question stem demands. Choice C is wrong because it contradicts what we know about the generator and the question stem. The question stem says negative charge builds up on the belt, but choice C says there's only positive charge? That's a pretty classic opposite answer choice there. And then choice D is wrong, even though it's the most commonly chosen wrong answer choice for this question, mostly because of the word shields. Shielding sounds like a really fancy term, but it's in the wrong realm here. Shielding is more so a term that's applied to electron orbitals, but this is more so electrostatics. And in any case, the whole point of conductors, and this entire dome is made of a conductor, the whole point of conductors is that they don't shield charge, they'll distribute charge. If there was an insulator involved, then maybe we could talk about shielding. But if you've got your science clear here, that'll help you eliminate choice D. So this learning goal has been, again, another angle of scientific reasoning. You will definitely run into some questions on test day that force you to incorporate new information to a theory, whether that is a theory you already know from your outside content or a theory that's given in the passage. And when you see those questions, you want to apply the same logic that you use to answer questions 5 and 6 to predict what those observations will do to those theories. So here we are in the fourth and final learning goal of this lesson. In the previous learning goal, you had a theory and had evidence and had to see how that evidence changed the theory. But in this learning goal, you are going to be making your own theories in a way. It's about taking information from a lot of different places to draw your own conclusions and then match those conclusions with an answer choice in most cases. These are the sorts of questions that are going to demand you take information from the passage, from your outline, from your science knowledge, and integrate all of it together to a single answer. As I'm sure you're familiar, these are very common questions on test day, which is of course why this is so important. We're going to be exploring this learning goal in the context of a passage, which is found on this page. There is a framework to write your passage map on the facing page, so take 3 minutes now to read this passage along with all the mechanisms and reactions and tables along with it, and then we will review the passage together. Alright, so this passage calls out its topic right at the start. It is all about lactic acidosis. And this paragraph, as with many first paragraphs, is a background on the condition. We get a description of it, that it involves low blood pH, which shouldn't be surprising because it's acidosis. Acidic means low pH. And then we see potential causes for this condition. Too much lactate production, not enough work on the liver, or something of those two put together. The last sentence is then a contrast to what happens in healthy individuals, and that the liver works pretty well in healthy individuals. A good label for this paragraph then is certainly to call out the name of the topic, lactic acidosis, and the description that's there, and then the fact that what this does at the end of the paragraph, which leads into the next paragraph, is that it is about normal liver function. And we're given the heads up that there are two mechanisms, which are pretty clearly labeled Mechanism 1 and Mechanism 2. Mechanism 1 is about the metabolism of ions. One thing that's really important to notice about this paragraph is, since we're saying we may increase or decrease metabolism, metabolism is itself a breakdown. So increasing metabolism of acid ions actually means decreasing the number of acid ions. That is a good label for Mechanism 1. There are then two reactions which are introduced in the paragraph for Mechanism 1 as the two pathways that lactate is metabolized. And that's confirmed by the fact that reaction 1 and reaction 2 both have lactate on the reactants side of the reaction. And that concurs with what we know about metabolism. If you have to break down lactate, then you're going to start with lactate and then you're going to end with no lactate. So that's what reaction 1 and reaction 2 are. And yes, it's good to outline every single little piece, even if it's just with a very small note like this one. And then Mechanism 2 is very brief, just calls out that plasma proteins can act as a buffer for hydrogen, which means it is a buffer for pH. Then in paragraph 3, an experiment is introduced. The experiment has a lot to do with Hartmann's solution, which we learn a little bit about in this paragraph. But as with many single paragraph details that you see in these passages, it's totally fine if you didn't know what Hartmann's solution was when you walked into this, and if you need to know about it in detail for a question, you can always come back to this paragraph. But the ultimate structure and outcome of this experiment is that the anesthesiologist, who is conducting it, gave these patients Hartmann's solution. The patients had lactic acidosis, but his final conclusion was that it did not actually treat what he wanted it to treat. And some experiments end that way. I'm sure you probably had that experience yourself. Here is a good label for this one. It sets up what the experiment is, and it writes down the conclusion. You're not always going to be given the conclusion so explicitly, but when you do, please write it in your outline. Then we have the final paragraph and a table that relates to it. The final paragraph expands on one concept introduced in the previous paragraph, which is the anion gap. It's called anion gap because it is the gap between, that's why it's got a minus sign in it. It is the gap between sodium ions and the chlorine and bicarbonate ions. A larger value means there's a larger difference between those two values. Similarly to what we saw about lactic acidosis in paragraph 1, we get a couple causes of strange anion gaps. We have one explanation for a low anion gap and another one for a high anion gap, which just happens to be our main topic, lactic acidosis. So a good label for this paragraph is here. Any good label is definitely going to call out that anion gap is mentioned. And this label actually writes out the formula. You've got sodium and you've got chloride and you've got the bicarbonate. It's ultimately okay if yours doesn't. The actual writing out of formulas in passage outlines can often be a matter of taste. Certainly if the formula is very complicated and very esoteric, you should not write it down because you can always refer back to it. But in cases like this one, where its ingredients are a little bit more familiar and the act of writing out the formula may help you understand it a little bit better, then it can be worthwhile. This passage then ends with the table, which is a little table that explains basically the scale of anion gaps. In the paragraph, we aren't given any numbers. If someone has an anion gap of 10, we don't know what that means, but once we get the table, we do know what that means. We learn that less than 6 is low, normal is 6 through 12, and high is greater than 12. So this passage as a whole, which is not particularly long but has a lot of items in it, is about lactic acidosis. Then we saw a couple of mechanisms that healthy livers usually use to regulate blood pH, along with a couple of reactions connected to the first mechanism. We had a paragraph about an experiment with Hartmann's solution that wasn't ultimately successful at coming to strong conclusions. And then we got more of an in-depth analysis of this anion gap number and a table that gave us some good benchmarks. So this is a good passage outline with which to move into the 4 questions on the following page. And while this passage is fresh in your mind, go ahead and do all 4 of those questions. Start with question 7 here, and then do questions 8, 9, and 10 as well. Give these your best shot, get to an answer for each one, and then we'll go over them. All right, so let's go over these questions now. Some of them were a little bit challenging. In fact, this one, question 7, particularly challenging. A whole lot to bring together, but it's going to teach us a lot about how the MCAT tests scientific reasoning. This question is actually in the exact same family of questions as numbers 3 and 4 from earlier on in this lesson. It asks us why a certain phenomenon is happening. The phenomenon is something that we are outright told in the passage, that the anion gap is really big in people with lactic acidosis, but the passage doesn't tell us directly why. We need to apply what we know from our science knowledge and various points of the passage to get the answer. And a good place to start is to go to paragraph 3. Question 7 calls out the anion gap, and we even have the formula for anion gap right here. It's the difference between positive sodium ions and the negative chloride plus bicarbonate ions in the blood plasma. From here, there are a couple things that we can do next. We could start going to the answer choices, reading them and eliminating them based on what we know, doing more research as necessary. But there's also another useful clue in the passage. Specifically, in paragraph 1, we learn that one main cause of lactic acidosis is limited hepatic metabolism, which means your liver doesn't work very well, or at least it doesn't break down things the way it's supposed to. At this point, it's fine to go to the answer choices and find one that can be either confirmed to be correct or get an answer through process of elimination. Starting with choice A, it starts out really well. It says hepatic function is limited. It's just a rephrasing of that line from paragraph 1. Choice A also says bicarbonate production is reduced. And to see if that's true, we can look at the reactions which are given to us in this passage. It turns out bicarbonate just so happens to be in the products of both of the example reactions given of breaking down lactate. So answer choice A at the very least seems to be true in that if the liver isn't working well, these two reactions won't be happening as often, and so less bicarbonate will get produced. But with questions like this, it's not good enough for the answer choice to just be true. It has to be true and also answer the question. So we also need to confirm that this reduction in bicarbonate production would increase the anion gap, because that's what the question is asking. Not only which of the following is true, but which of the following is true and explains an increase in the anion gap. And as it turns out, the anion gap equation has bicarbonate in it as well. So if we have a reduction in bicarbonate, since there is a negative sign before the term that has bicarbonate in this equation, less bicarbonate is going to lead to a larger final product, anion gap. That means every single step of this has been connected, and choice A is indeed correct. Now, just in case this wasn't the exact process you went through and you weren't totally sure about choice A, let's confirm that the other choices are wrong. Choice B is wrong because there is no connection to serum albumin in relation to lactic acidosis in the passage. Albumin levels are mentioned, but we never actually get the line or even the inference that lactic acidosis necessarily means you've got a lot of albumin. The same thing applies to choice C. Urine volume is not mentioned in this passage at all. It's an outside the scope answer choice. Interestingly, choice C as a statement is consistent. If urine volume did increase, it would reduce levels of sodium. But even if it did reduce levels of sodium, even if lactic acidosis does increase urine volume, that would actually lower the anion gap, because we'd be reducing a positive term in the equation, not raising the anion gap. And choice D is kind of similar to choice B in that it is a faulty use of detail. Citrate and gluconate are mentioned in the part of the passage connected to mechanism 1, that their levels of metabolism are a way that the liver regulates blood pH, but there's no connection made from that to lactic acidosis necessarily. Remember, the mechanisms were about normal liver function, not about liver function under lactic acidosis. So, holy cow, there is actually a lot to bring together to answer that question and get it right in a robust and confident way. There were 3 different locations in the passage, all of which had to get synthesized in order to come to this correct answer. Plus, you had to synthesize it with your knowledge of science, the liver, how to read equations, and so on. So, as the Kaplan tip says at the bottom of your screen, these are the questions, and remember, these types of questions are really common, 45% of each science section, that will require you synthesize from multiple points in the passage. That is what the AAMC does for these questions, so you gotta be prepared for it. And when you see questions like this in your practice, you've got to focus on them and make sure you're getting them right for the right reasons. Let's move on to the next one. Question number 8 gives us a normal situation that normally the measure for lactic acidosis is serum lactate level, but then asks why this might not work so well for the experiment that we see in the passage. Again, it's giving us a phenomenon, saying this doesn't work very well, and asking us why. What is the cause of this phenomenon? So if we go to the research here, experiment is paragraph 2, and if we go to paragraph 2, it tells us what Hartmann's solution is actually made out of. And, well, look at that. Hartmann's solution includes this crazy looking molecule, which you might not know the name of unless you look at the parentheses right after it, where we find that it's called sodium lactate. That lactate, the second half of sodium lactate, is the same lactate that we usually use to measure lactic acidosis. So the correct answer here is C. Hartmann's solution itself actually adds a whole lot of lactate. So if you test a patient and they have really high serum lactate, you don't know if that's from lactic acidosis or if it's from the sodium lactate you just gave them and injected into them. That's why it's not going to be a good measure for this particular experiment. Again, this is about the synthesis and reasoning of information from the question, the answer choices, and the passage all together. Question number 9 then gives us a situation of a blood sample and then asks us something about this blood sample. Specifically, what do we know about the hydroxide concentration? Now, this question is in the same world as this passage. It's about acids and bases and serum concentrations, but it never actually references the passage or requires any knowledge from it, so it's what we call a pseudo-discrete question. Now, that doesn't necessarily mean it is easier, but it does mean your performance on it will be fairly independent of how well you were able to understand and outline the passage. That means we should focus on the question stem itself to see what we can conclude about this sample and its hydroxide concentration. The question stem tells us that the pH of the blood is below physiological pH. Remember, lower pH means higher acidity, higher hydrogen, less hydroxide. So the clearest prediction we can make here, and it's a pretty clear one, is we should look for an answer that means low levels of hydroxide, because that's what lower pH means. And the correct answer here is C. Choice C is putting a maximum value on OH concentration. If you're putting a maximum value, basically an upper limit on something, then you're saying it's going to be at that level or less than that. And this concentration of hydroxide is about physiological hydroxide levels. This 10 to the negative 7th should be a good clue to that, even if you don't have that number memorized. Another way of saying choice C is we know the hydroxide level has to be below normal hydroxide levels, which is basically just a rephrasing of what the question sim gives us in the first place. There's one answer choice to be particularly careful of, which is choice A. Choice A is along the same lines as choice C. It says it, meaning the hydroxide concentration, is less than the hydrogen concentration. But physiological conditions are at a slightly basic pH, so even if, as the question stem says, the pH that gets measured is more acidic than physiological pH, that doesn't mean it is an acidic pH, which is what choice A is saying. Choice A is saying hydrogen is greater than hydroxide, that would mean an acidic pH. But since the body starts at a basic level, you can get more acidic while still being basic overall. That's why choice A is wrong, and it's definitely the biggest trap. Choice B is wrong because it does the opposite of choice C. We already said choice C is correct because it puts an upper bound, but choice B puts a lower bound, a minimum value, which is implying that OH could actually be really high, which is the opposite of what the question stem says. And then choice D is wrong because, well, it's not impossible to make any judgments. We've just made a judgment. We know that hydroxide concentration has to be less than at normal physiological levels. That's why choice D is wrong. And last but not least, question 10. Not like some of the other questions in this lesson, this one goes on for a while, goes all the way to the bottom of the screen here. But as with all long questions like this, we need to attack it piece by piece, make the connections we need, and get to an answer. The first thing question 10 tells us is another detail about the patients in the study, which is why they developed lactic acidosis, that they have hypoxia. And if you don't know what hypoxia means off the top of your head, you could make an inference that hypoxia means low oxygen. Low oxygen means that cellular respiration is going to get shunted over to the anaerobic pathway, which is why we're given this reaction. This reaction is what happens to pyruvate after glycolysis. When there isn't enough oxygen available, we're then given some ratios in the rest of the question stem, that we have a normal lactate to pyruvate, and then what the patients have, lactate to pyruvate. The takeaway here is that patients have a whole lot more lactate in relation to pyruvate than regular folks. And at the end, the question asks us which of the following most likely to be true. The answers, though you won't read them all the way in the assess step, mention ratios and some of the substrates involved in the reaction. And as you actually get to the answers and read through them, try to eliminate them, find a match, you want to activate all your knowledge of the biochemistry involved, general chemistry involved, and the answer ends up being A. Let's see why. Remember that low oxygen in the anaerobic pathway is going to lead to a buildup of NADH and pyruvate. The pyruvate's got nowhere else to go because it's not going to go to the citric acid cycle when there's no oxygen. But because of that buildup, that means this equation in the question stem is going to shift to the right, meaning it's going to be more of the stuff on the right side here than there would be if oxygen were available. This is confirmed by the question stem, the fact that folks who have this hypoxia have much more lactate, 20-to-1 ratio, than normal folks do. They only have a 10-to-1 ratio. And that entire story there is more or less answer choice A in a nutshell. Choice A describes the high levels of lactate, which we already know are there, and says those high levels are caused by a buildup of NADH. That's exactly what's going on here. In fact, it's an interesting little intersection between the biochemistry of cellular respiration and Le Chatelier's principle from general chemistry. More reactants will shift the reaction towards the product. Now, as for the wrong answers, choice B is wrong because even though the first half of it is correct, there are in fact low levels of pyruvate, relatively speaking, for the patients. Choice B says they're driven by reduced rates of glycolysis. However, what you should remember from cellular respiration is that when there's no oxygen, there's actually going to be higher rates of glycolysis, because glycolysis is the part of respiration that doesn't require oxygen. Basically, choice B kind of mentions Le Chatelier's principle, but it's got the wrong link in the chain. Sure, reduced rates of glycolysis would lower levels of pyruvate because pyruvate is a product of glycolysis, but we know that's not happening here because of our outside science knowledge. Choice C is wrong because even though it's got the ratio of thing on the right to thing on the left, which could be a step in the right direction because when a reaction shifts, the left goes up and the right goes down or vice versa, this choice has it opposite because it says that would have to be less than the ratio rather than what we know needs to be more than the ratio of normal folks. And choice D does the exact same thing. It is a ratio of thing on the right to thing on the left, but it gets it backwards because it says less rather than greater. This question is great to finish up this lesson on because it, just like many of the questions before it, requires a lot of critical thinking and integration of information from different places throughout the passage, in the question stem, and in your brain with your science knowledge. So let's briefly review how we saw these learning goals in action. Skill 2 questions about scientific reasoning are going to involve taking scientific principles or a specific theory or model that's given in a passage or a question, and it's going to ask you to do something about them. It might ask you to explain them. It might ask you to evaluate them, saying are they good or are they bad. You might see new observations or information, ask how that affects them. We saw examples of all of those in this lesson. We also saw that in order to get to the right answer for these questions, it involves appreciating the concept of a scientific phenomenon. That often a situation, a science-y thing is described, and we need to say, why is it happening? Or what might happen next? We also might be asked, hey, is it likely that this happened at all in the first place? Or if a scientist is saying this happened, or if it happened for a reason, how valid is that explanation? So if you made it through the questions in this lesson with a good idea of why the right answers are right and the wrong answers are wrong, then you're really on the right track to perfecting this skill. keep in mind that MCAT scientific reasoning, it has a really general name. That's because it's a very general skill. It's a big skill. The thing about the big skill, though, is that it's going to get you a lot of points. And so whenever you see questions like the ones you saw in this lesson, you want to use the same principles and tactics we saw in this lesson to solve them, and you're going to get a whole lot of points in the science sections on test day.